Welcome to the lecture for week 9. This is topic 1, and we are introducing metamorphic rocks. Metamorphic rocks are the only main type of rock we haven't discussed yet in this course, and that's partly because they're less common on the surface, and partly because they are, in some ways, the most complicated. So let's review the rock cycle. Remember, there are 3 groups of rocks: igneous, sedimentary, and metamorphic. Igneous rocks are crystallized from cooled magma or lava. Sedimentary rocks are made of pieces of other materials. And finally, metamorphic rocks are other types of rocks that have been altered by heat, pressure, and/or water to create something new. So metamorphic rocks are rocks that result from the alteration or transformation of pre-existing rocks by heat and pressure and/or fluids while remaining solid. Meta means change, and morph means shape or form. So these are rocks that have been changed in their shape or form. The original material, or parent rock, that was there before metamorphism occurred is called a protolith. The processes of metamorphism change the mineral components and/or texture of the rock. For example, we can start with a protolith, or parent rock, of a red shale. That incorporates the minerals quartz, clay minerals, and maybe iron oxide. After it undergoes metamorphism, we end up with a metamorphic rock, let's say gneiss, which contains quartz, feldspar, biotite, and garnet. The constituent minerals have changed from the red shale into new minerals, and a new texture has been imparted on the crystals of the rock. So let's review what minerals are, because a metamorphic rock contains different minerals from its protolith, but retains a similar overall total composition. A mineral has to be naturally occurring, a solid at room temperature, it has to be inorganic, so no carbon to hydrogen bonds, it has to have a fixed chemical formula of natural elements, and it has to have a specific crystalline structure. Here we've got feldspar and quartz, 2 examples of common minerals. Let's talk about that specific crystalline structure part. Sometimes when a mineral forms under different conditions, its crystal structure can be altered. Here we have 2 different versions, or polymorphs, of quartz. These are the same mineral that contain the same chemical elements, but the crystal structure is slightly different. Quartz is made up of these 3-sided pyramids, which are called tetrahedrons, and they are all latticed together to create the crystal structure of quartz. Alpha quartz, which is the main version of quartz you're likely to encounter here at the surface of the Earth, can also be transformed into beta quartz when it crosses a temperature threshold of about 573 degrees Celsius. This temperature change forces these crystal tetrahedrons to rotate 180 degrees and create beta quartz. Another example of metamorphism due to the change in pressure would be the conversion of granite, carbon, to diamond, also carbon. Both of these minerals are polymorphs of carbon. We have graphite, which is composed of these sheets of carbon hexagon structures. If you subject graphite to extremely high pressures, you compress it and it turns into diamond, which has a cubic structure of these carbon atoms. They are both carbon, but they contain different crystal structures and are therefore different minerals. A bit more of a complex example that has more relevance to metamorphic rocks are the polymorphs of aluminum silicate, Al2SiO5. These are common index minerals, which is a mineral that we use to track the maximum temperature and pressure combination a rock has experienced. All 3 of these minerals, sillimanite, andalusite, and kyanite, are all made of the exact same stuff, aluminum silicate. But they all exist in different realms, different regions of the temperature to pressure relationship chart. And they are separated by these lines called phase boundaries, which are exactly the same as phase boundaries between states of matter. If, for example, at low pressures and low temperatures, a bunch of kyanite forms in your metamorphic rock, and then you heat the rock up a whole bunch, you will eventually form andalusite, and if you heat it up even more, you will form sillimanite. So in the crust, metamorphism occurs under pressure and temperature conditions between those of sedimentary processes, which is the process we call lithification, and melting. Geologists use descriptive grades to describe the pressure and temperature conditions that a rock has experienced. In this chart here, we can see that the conditions a rock goes from extends from lithification, which is the process that turns regular sediments into sedimentary rock, all the way up to partial melting of rocks, forming granites. A metamorphic rock that has experienced relatively low pressures and temperatures would be considered a low-grade metamorphic rock, and a metamorphic rock that has experienced high temperatures and pressures is called a high-grade metamorphic rock. Here are some examples of the progression of low-grade to high-grade metamorphic rocks. On the upper left we have shale, which is just a sedimentary rock composed mostly of mud, that is silt and clay. If you slightly metamorphose it, you get slate, which is a low-grade metamorphic rock. If you increase the metamorphism more, you get phyllite, then schist, and then ultimately gneiss, which is the highest grade of metamorphic rock. The sedimentary rock limestone under metamorphosis becomes marble. Sandstone can become quartzite, and basalt will go to greenstone and then ultimately to schist. So let's talk about the agents of metamorphism. Let's start with temperature. Temperature causes atoms in the mineral to vibrate more rapidly. Atoms form new mineral structures that can survive this increasing vibration. And if you add enough heat, the structure cannot remain solid and it melts. Recall the geothermal gradient, the relationship of temperature and depth in the inside of the Earth. So under most conditions, your temperature will increase as your rock gets buried deeper and deeper into the Earth, therefore also experiencing increasing pressure. But as we'll talk about over the course of this lecture, there are conditions where that isn't always the case. Our next agent of metamorphism is pressure, which is the force exerted over an area on a material. Pressure that affects metamorphic rocks can be grouped into confining, also called lithostatic pressure, and directed stress. Increased confining pressure will cause the atoms in a mineral to be pushed closer together. These mineral structures then rearrange to become more compact. So confining pressure makes a material want to become smaller and take up less volume. In confining pressure, the stresses on all sides of your material are equal. Directed stress, on the other hand, has a dominant stress, which can produce either pure shear, which is single direction compression, or simple shear, which is a rotational force that causes your mineral to deform. Directed stress leads to foliation in most minerals and rocks. Foliation, which is our new featured word for this lecture, is the dominant alignment of minerals in a metamorphic rock. So let's start on the left here. When we have pressure, a directed stress that has a dominant force direction, the mineral grains in that rock will want to recrystallize or form new minerals in response to pressure. As pressure and temperature increase, continued recrystallization and formation of new mineral assemblages occurs. This causes your minerals to grow along directions, dominant planes that are perpendicular to the main direction of stress. On the upper right, we see a bedded sedimentary rock, and let's say it is experiencing a dominant stress from the upper left and lower right corners. As that dominant stress increases, the mineral grains in the sedimentary rock will want to regrow perpendicular to that axis of dominant stress. This forms foliation, and with enough heat and pressure, those minerals will recrystallize and form large bands. You can see this process really well in this coarse-grained granite in the lower right, and with directed stress and a lot of heat and pressure, your granite will recrystallize and form this nice banded metamorphic rock called gneiss. Our final agent of metamorphism is fluid. Chemically reactive fluids, which are made up mostly of water and dissolved carbon dioxide, move through rocks as either thin films of fluid between individual mineral grains, or it can be larger amounts of hot water moving through rocks. This is a process called hydrothermal alteration or metasomatism. This process is very similar to chemical weathering, and really it is just a different variety of chemical weathering that occurs under higher pressure. A very common example of hydrothermal alteration occurs along mid-ocean ridges, spreading centers. Ocean water seeps into the new oceanic crust, where it is then heated along the mid-ocean ridge, and the ocean water gets circulated through the basaltic oceanic crust. This causes hydrothermal alteration of the basalts, and reorganizes the minerals and introduces new elements into the crystal structure of the basaltic crust. In particular, this introduces minerals containing sulfur, called sulfide minerals, into the basaltic rocks, transforming them into new minerals called serpentine. You may have heard of undersea vents called black smokers, which introduce superheated mineral-rich fluids into the lower depths of the ocean, creating these towers of bizarre minerals above the basaltic crust. If we look at this closer on a mineral-by-mineral basis, we start out with olivine and pyroxene, which are the primary minerals in basaltic oceanic crust. If we add water to that, we end up with serpentine plus free hydrogen plus methane and heat as a result of this chemical reaction. Down below are two versions of serpentine. On the lower left we have serpentinite, which is a higher pressure version of basalt that has been subjected to hydrothermal alteration. And on the right we have just a big chunk of serpentine. It's got this kind of waxy green appearance. Now let's move into different types of metamorphism. Let's start with burial metamorphism, the most simple kind. This is a low-grade metamorphism that occurs as rocks are buried over time. This results in increased pressure and, to some degree, increased temperature. This primarily occurs in deep sedimentary basins, where sediments have been piling up for a very long period of time, producing a very thick stack, which therefore increases the pressure on the lower part of that big stack of sediments. On the right, we can see a progression of this. Let's say a thick package of sediment is buried to 2 kilometers deep. That's not very much pressure, geologically speaking, but it does result in some increase of temperature. As more sediment is deposited, the depth gets higher, as does the temperature, which increases at 8 kilometers depth to about 170 degrees Celsius, which is approaching the conditions that are considered metamorphic. Over even more time, even more sediment is deposited, and let's say that it is buried to about 12 kilometers deep. This raises the temperature to about 240 degrees Celsius in most parts of the world, and this is considered low-grade metamorphic conditions. In the middle, this low-resolution diagram shows the progression of peat, which is just compressed organic matter, into lignite, which is a very low-grade coal. With greater pressure, we have a soft coal called bituminous coal, and in low-grade metamorphism, that low-grade coal will become very hard anthracite coal. This is also how we get shale turning into slate, and sandstone turning into quartzite. Again, these are some rocks that you often find in burial metamorphism conditions. Peat goes to lignite. We have brown, loose, soft material going into a slightly harder, blacker material. That becomes bituminous coal, and then it becomes anthracite, which is a shiny, angular, bizarrely fractured, very high-grade coal that we use a lot in power plants. On the left we have quartzite, which is just what happens when the quartz grains in a sandstone begin to recrystallize together and become a little bit harder. Our next type of metamorphism is contact metamorphism. This occurs over a small area close to a pluton. So these are conditions that are low pressure with variable temperature, occasionally very high temperature. The area around an intruding pluton where contact metamorphism occurs is called a metamorphic aureole. Contact metamorphism is essentially the surrounding rocks being baked under low to moderate pressure by an intruding body of very hot magma. That baking action of the surrounding rocks remains after the magma has cooled and solidified, and has left behind a zone of metamorphism called an aureole around that pluton. The metamorphic rocks produced during contact metamorphism depend on the protolith that is present at any given location, but in all cases the grain size increases with metamorphic grade. Shale and basalt will be metamorphosed into a rock called hornfels, sandstone will be baked into quartzite, and limestone will form marble. This somewhat complicated diagram on the left shows this in a little bit more detail, including the different types of minerals you are likely to see in certain conditions. Here are two of the common contact metamorphism rocks. We've already talked about quartzite, so here on this slide we have hornfels on the right, which comes from shale and basalt, and on the left we have this nice tightly folded marble, which results from limestone. This example is just inside Kings Canyon National Park in California, where large bodies of limestone were contact metamorphosed as the Sierra Nevada batholith was intruded over millions of years. That action baked and deformed the limestone, transforming it into this beautiful marble exposure. Our next type of metamorphism is regional metamorphism. This is metamorphism occurring over a very large region, usually associated with mountain building or orogeny events during continental collisions. We'll talk about this a little bit more in the Topic 2 lectures. At convergent boundaries, we have compressional stresses, thrust faults and reverse faults, folding of the bedrock to form synclines and anticlines. We get regional metamorphism and therefore rocks that are foliated, because there is a directed stress of compression in these continental collision environments. In the lower right, we have a temperature-pressure diagram, where instead of pressure we have depth in kilometers. And these different regions that are colored in this chart show the different regions of metamorphism that are defined. We'll talk about these more as well in the Topic 2 lecture. But in this plot, the green dashed line is the general trajectory most often seen in continental collision environments. Low-grade metamorphism includes zeolites and clays. Intermediate grade metamorphism will form rocks called schists, phyllites, and green schist. Higher grade we have gneiss, and with partial melting from extreme burial pressures and temperatures, we start to get partial melting, partial recrystallization of the rocks, forming something called a migmatite. These are some of those common rocks you see in continental collision environments. On the upper left we have a phyllite, which has a distinctive wavy texture to it. This is a very fine-grained metamorphic rock with very strong foliation that is enhanced by very tiny, microscopic, in fact, mica crystals. This is a low-grade metamorphic rock. Our intermediate metamorphic rock for this condition is called a schist. It's typically medium-grained and strongly foliated, usually with lots of large grains of mica, quartz, and sometimes garnets. This is our intermediate or medium-grade metamorphic rock. And on the lower right we have gneiss, which is a very coarse-grained metamorphic rock with very coarse banding rather than just foliation. When you compress rocks enough, their foliation goes from individual minerals to wider bands of minerals. This is a high-grade metamorphic rock. So what happens when we increase pressure and temperature even further beyond gneiss? Well, that's when certain minerals, primarily quartz and some of the feldspars, actually start to melt. This produces a partially molten rock that we call a migmatite. It's usually highly deformed and has pockets of very large, coarse crystals of quartz and feldspar. But if we increase the pressure and temperature even just a little bit beyond migmatite, then we get an igneous rock, and that is granite. So migmatite is a borderline metamorphic and igneous rock. Some of the minerals in that rock have remelted and re-solidified, while others have not. Other minerals just survive the process. Until, that is, you increase temperature and pressure further, which causes all of the minerals to melt, your rock melts and forms an igneous rock, a pluton. Our next type of metamorphism is that which occurs in subduction zones. Subduction zone metamorphism is sort of a type of regional metamorphism in that it occurs along the length and width of a subduction zone environment. So these occur over a great distance along the margins of a continent. Subduction zones are often characterized by low temperature, high pressure metamorphism of oceanic crustal rocks, which are basaltic in composition. We also see associated high pressure, high temperature metamorphism inside the volcanic arc. So our dense oceanic crust remains cold as it sinks into the mantle because it's very dense and it has a very high what we call heat capacity. It doesn't like to change its temperature. So it experiences relatively low temperatures under very high pressures as it sinks deep into the interior of the Earth. But as melting is produced coming off of that subducting oceanic plate, in the associated magmatic arc we get high temperature, medium pressure metamorphism occurring in the continental crust around the zones of magma intrusion. If we look at all of these diagrams, we see dashed lines which reflect lines of equal temperature. And if you look closely at these, you can see that these lines of equal temperature curve because the inside of that subducting oceanic plate doesn't like to change its temperature, so it retains its temperature even as it sinks deep into the Earth. This produces areas of low temperature, high pressure metamorphism that we call blue schist metamorphism. And that occurs inside the subducting oceanic plate. Blue schist is what we call a facies as well as a rock type. A facies is a set of conditions producing certain mineralogy and structures. We'll talk about facies in greater detail in the Topic 2 lecture. Deeper and hotter than a blue schist facies is called eclogite, which we rarely find on the surface, and we'll talk about in more detail in the next lecture. On the left we see a blue schist. The blue color comes from the mineral glaucophane. And on the bottom left we have a very funky looking rock called eclogite. Very dense, very heavy, contains a lot of green minerals as well as these red minerals which are garnets. Final type of metamorphism is called fault metamorphism. This is also known as dynamic or shear metamorphism. If you think back to our faulting topics, we start with non-metamorphic faulting, which is what we find in the upper brittle crust. This produces features called fault gouge and fault breccia. And along faults in the upper crust we often see hydrothermal alteration. But as you get deeper and the pressure and temperature increases, we get below the brittle crust and into the ductile crust. Just like a glacier has a brittle zone and a ductile zone, the crust has that as well. And when we get into the ductile crust, we stop getting faulting and start forming things called a myelinite. So whereas in the upper crust a shallow fault zone results in breakage of rocks, myelinite is a zone of sheared, kind of stretched rocks along that same fault zone. In the upper brittle part of the crust, the pressure and temperature are too low for metamorphism, so the rocks break, producing a fault breccia on the upper right, and a fault gouge, which is a planar zone of sheared clays and silts and broken up rock that we call fault gouge. Deeper along the fault, the rocks deform plastically. So you get a metamorphic rock with kind of smeared out, plastically deformed mineral grains. They appear similar to foliated rocks, but the minerals are aligned by stretching and strain rather than directed pressure. By looking at this rocks, you should be able to see the sort of linear fabric sort of a pattern in these crystals, and that's because they have been stretched, smeared, and overall plastically deformed, and you can see this really well in the one on the lower left. On the lower right, we have a nice stretched, elongated quartz crystal surrounded by very small grained mica crystals. Finally, we have shock metamorphism. This is very uncommon, but it is important. This is also called impact metamorphism, and it is an environment of extreme pressure and temperature that occurs in one environment only, and that is during meteorite impacts. So whereas normal metamorphism will occur at temperatures roughly from 1,000 degrees Celsius to about 200 degrees Celsius, and pressures of 100 megapascals up to about 4 gigapascals, shock metamorphism will occur up to about 3,500 degrees Celsius and with pressures over 100 gigapascals, much greater than anything you find anywhere near the surface of the Earth in any other condition. When your meteorite or asteroid impacts the surface, you get extreme pressure and extreme temperature that shocks and deforms all of the minerals and rocks that recrystallize very rapidly. On the upper left, we see the most distinctive shock metamorphism mineral, which is called shocked quartz. It has this distinctive texture to it, as well as these zones. These different colors are formed by polarized light. That is a topic called optical mineralogy, which we are not going to touch in this course, but that is why this has different colors. The regular shocked quartz looks basically no different from regular quartz. And that is it for our introduction to metamorphic rocks. Stay tuned for the Topic 2 lecture on the different metamorphic environments or facies.